Okie dokie, boys and girls, minions big and small, you're here to do some maths with me, Nick. We are exploring a cheeky step question, but really what it's about is some slightly high level maths, which is super cool, which is about Laplace transforms, something that is standard in a first, second year undergrad course for maths. But here it is popping up in a step question, because really you do have the maths ability to access it. So what is a Laplace transform? So a Laplace transform is a transformation of a function. You change one function into another one. And it's defined like this, capital F of S. So if we transform little f, here we're using the variable t. The variable doesn't really matter, but so the Laplace transform of little f is called capital F, and it's this integral. So it's e to the minus st f of t dt. So importantly, s is the variable that will be left. All right? And t is my dummy variable in here. Okay, so if I want to transform any function, I get this. We're going to find a lot of these ones, but so for example, right, I'll just do one quickly. The Laplace transformation of just the function t, right, t, just t, is, all right, the straight line, y equals x. That would be 0 to infinity e to the minus st times t dt. We can do integration by parts, differentiate the t, integrate to the e to the minus st, so that is t e to the minus st the minus s between 0 and infinity, plus the integral of e to the minus st over s from 0 to infinity dt. Now at infinity, this requires a little bit of knowledge, L'Hopital's rule maybe. All right, so you get t goes to infinity, e to the minus st goes to 0, and this 0 is more powerful than that infinity. That's just something I know. And when I plug in 0, that's 0. So all of this goes to 0. So I'm left with this bad boy, which is over s squared between 0 and infinity, which is, again, at infinity, that dies away, so it's just 1 over s squared. So, right, there you go. That's an example of a Laplace transform. This transforms the function t, right? F of t goes to f of s, so t goes to 1 over s squared. Undoing a Laplace transform is actually quite tricky. A lot of the time we just rely on recognizing what it is, right? So if I see 1 over s squared, I know that that is the transformation of t, for example. Let's jot that down somewhere actually. I quite like that. Hopefully I got that right. Otherwise, someone's going to be editing a big chunk out of this video. Right, none of that is actually the question. But so what we want to do is be able, we don't want to do this fully from scratch. Instead, basically what we've got here, what this step question is doing is saying it's introducing the idea of what a Laplace transformation is. All right, and we've just done one, right? The transformation of t is 1 over s squared. But we're going to find a bunch of rules. So what happens if I multiply my function by an exponential? So all of these are going to be expressed in terms of f of s, all right? So this is my starting function f. If I transform f, I get capital F of s. And let's see what any of this does, parts A, B, and C. Right, so we want to transform e to the minus bt f of t. So we go 0 to infinity, e to the minus st, e to the minus bt f of t dt. Well, that is, do you know what? Space, 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 space. That is the integral between 0 and infinity of e to the minus s plus bt f of t dt. But that, all that is exactly this, just instead of an s, I've got an s plus b. So that is capital F of s plus b. Okay, fine, fine, fine. What does that mean? So for example, if I want to find the Laplace transform of, I've already done it with t, right? So e to the minus bt t, I don't have to do that from scratch. I know it's the transform of t, which is 1 over something squared, but evaluated at s plus b. All right, but evaluated at s plus b. So that's nice. That's nice. We do also need to point out that s needs to be positive. Now, why does s need to be positive? By and large, when I did it for the transformation for t, you'll notice I just went e to the minus st disappears at infinity. That's because that was e to the minus infinity. That was predicated on s being positive, because minus positive t. Go have a look back at the video, right? I made the assumption there that s was positive. And for the same reason, I need b to be positive, because I need this e to the minus gubbins t, I need that to disappear at infinity. So I need all of this, I need this term here to be positive. All right? So for example, I can quickly get that one. So that's a nice rule to have. Wicked. How about b? What if I want to transform something times t? Well, let's just plug it in. That is the integral from 0 to infinity, e to the minus st of f of at. Now, what am I going to do here? Well, let's just make a change of variable. U is equal to at, du is a dt. And when t is 0, a times 0 is 0. When t is infinity, a times infinity is infinity. And again, I'm making the assumption that a is positive because I don't want it to muck about with my limits of integration. I don't want it to muck about with that. So there are some limitations on these that we can fix. But what does this become? I'm going to pick up a 1 over a. Well, let's just plug it all in. So my limits don't change. I get e to the minus s u over a, rearranging this for t, f of u du over a. Well, if we pull this a out, if I pull that 1 over a out, so let's, boop, what have I left? Well, again, u is just a dummy variable. U could be any variable you want. It's just, right, it's just a dummy integration variable. So it could be t's for all we care. It doesn't really matter. So basically, this is just the transformation, but instead of having s's, we've got s over a. All right? So again, let's apply that to our example down here. If I want to find the Laplace transformation of 2t, for example, that would be 1 over 2. And then the transformation of t, which was 1 over something squared, but instead of being evaluated at s, it's evaluated at s over 2. So in fact, I think that comes in at 2 over s squared. And in fact, if I want the Laplace transformation of mt, I think basically what I get is m there, and m there. So I get an m over s squared. So there you go. That's nice. Again, so this is what these rules are used for. And at the end of this video, I will try and show you a really cool application of Laplace's transform. All right, there is a brother of it called the Fourier transform, which you might have heard about. That's used a lot in signaling. But really, they're just really cool transformations. Love them. Right, now we want to transform f dashed of t and f double dashed of t. Right, so that is 0 to infinity, e to the minus st, f dashed of t dt. Well, we're going to use integration by parts. We're going to use integration by parts. Let me set this up here. So we're going to differentiate e to the minus st, and we're going to integrate f dashed of t. So if I differentiate that, I get minus s e to the minus st. If I integrate the f dashed, I get f of t. Simples, all right. So that is equal to plus minus, and I'm going to want this bad boy, and then the bottom bit. Right. So what do I get? I get e to the minus st f of t at 0 and infinity plus s times the integral from 0 to infinity e to the minus st f of t dt. So I need to plug in 0 and infinity. Now here is where it says a suitable function f. Because what I want this to disappear at infinity. So e to the minus infinity is dini 0, and then f of infinity. So what I need by a suitable function is I need a function that doesn't blow up at infinity, or at least I need one that doesn't get bigger faster than an exponential. All right, so we do have some limitations there on this transformation. All right, nothing is perfect. But we're just going to assume that in infinity it goes away, because that seems fair. So I get 0 minus, let's plug in 0, that's f of 0. And then this is plus s, and that is just the transformation of s. All right, so the 0 doesn't do anything. Is that the correct answer for me? Yes, yes it is. All right. And then finally, before we get on to this crunchy stuff here, how about if we do this exact same exercise with the second derivative? Well, we're going to do integration by parts again, but we're going to have to go twice. So differentiate that, minus s e to the minus st, differentiate again, s squared e to the minus st, integrate that one, integrate that one. Let's put our pluses and minuses in. Let's go diagonally, and then we'll have our bottom one. So what do I get? I get e to the minus st f dashed of t minus minus plus s e to the minus st f of t to 0 and infinity plus, and I'm going to shortcut this a little bit just to save space. I'm going to get the s squared, the integral of e to the minus st ft, which is just my f of s. So now we just need to deal with this. And again, we've got the same condition. S has to be positive so that e to the minus st disappears at infinity. And I need it to win out. I need it to win out against f dashed, and I need it to win out against f. So this is what it means by a suitable function. Not all functions will behave properly for me. Well, now we're going to plug in 0. So we get minus f dashed of 0 plus, no, minus s f of 0 plus s squared f of s. Okay. So I'm going to make a little repository of all of this. Right? I'm going to make a little repository. Let's go up here. S plus b. So the Laplace transform of e to the minus bt f of t is f of s plus b, where again capital F is just the transformation of little f. The Laplace transformation of f of at is 1 over a f s over a. And the Laplace transform of f dashed of t is s capital F of s minus f of naught. And the Laplace transformation of f double dashed of t is s squared f of s minus f dashed of naught minus s f of naught. Okay, so that's my combo wombo. And there are a bunch of rules like this for different things you can do Laplace transforms of. Right, D. Let's transform sine t. So e to the minus bt sine t dt. Now, sine t behaves beautifully. It's stuck between 0 and 1, so e to the minus st will win out at infinity, no problem there. And its derivative will as well, sine t becomes cos t, so that's nicely and well behaved. So I need to evaluate this. And again, let's do a bit of differentiation by parts. We should be used to it. I don't really care which way we go. Minus b e to the minus bt, sine integrates to minus cos, and we get b squared e to the minus bt. That becomes e to the minus sine t. So that tells me that f of s is equal to plus minus plus. We get minus e to the minus... why have I put b's in here? What is actually wrong with me? Where did the b's come from? Did I have a minor stroke when no one was looking? Don't know. Right, e to the minus st cos t, going along diagonally, and then minus 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 is a minus s sine t e to the minus sine t between 0 and infinity, and then minus s squared f of s. Standard trick, really, that you should know from your A-level of how to find the integral of e to the minus x sine, or anything to do with e to something in sine. It's a very, very straightforward one. 1 plus s squared f of s is equal to... now, at infinity, he goes away, because again, e to the minus infinity wins against cos, and it wins against s, and it wins against... Well, no, s is just fixed, actually, so it wins against the sine, so no problem. How about at 0? E to the 0 is 1, cos to the 0 is 1, minus minus 1, so I get a 1. And at 0, sine of 0 is 0, so that's all I get. So in fact, I get f of s is 1 over 1 plus s squared. So that's nice. That's nice. Let's just add that up here in case I lose it. So we know now that the Laplace transformation of sine t is 1 over 1 plus s squared. Whoop, whoop. Right. What we want to do is find the Laplace transformation of all of this gubbins. So what I suggest is let's first find the transformation of cos. All right, actually, let's make a bit of space. A little bit of space, because otherwise it's going to be super cramped. My handwriting is terrible at the best of times. So, what about cos t? Well, the Laplace transformation of cos t, and we're going to use this, because cos, that is the Laplace transformation of sine t differentiated. Okay, so that is going to be s times f of s, which is 1 over 1 plus s squared, minus f of 0 minus sine of 0, which is 0. So that is s over 1 plus s squared. Cool. You know what? I'm going to make another note of that. And finally, we need to do it with cos of qt. So now we are cooking with gas. What do we say cos of? So we're putting in a in front of it. So I'm going to get 1 over q times f of s over q. So I get s over q, 1 plus s over q squared. So what do I end up with? I think that ends up with s over q squared plus s squared. With a little bit of algebra, I think you get that. Yes, that's a q, leave me alone. Because that q comes there, goes in, yeah, we're good. So finally, the Laplace transformation of e to the minus pt, cos of qt. Use that one. It's this bad boy, but at s plus b. So it will be s plus p over q squared plus s plus p squared. And I can tell you now that would not have been pleasant to do from scratch. This is much, much nicer. So there we go. There we go. I think that's plenty enough of me rambling on this video for today. We might revisit this in the future and show you how you can solve differential equations using a Laplace transform. Wicked. Don't forget to comment, don't forget to subscribe, like if you enjoy this video. Hit the notification button if you want to know when the next one is coming out, normally about every other day or so. I'm Nick, I hope you enjoyed this. Keep doing maths.